Hi everyone! In the previous video, we developed a Python program that automatically analyzes a single Winston-Lutz image. The program detects both the radiation field center and the ball bearing center, then calculates the offset between them. Today, we'll take the next step. Instead of analyzing one image, we'll combine multiple Winston-Lutz images acquired at different gantry angles to estimate the three-dimensional radiation isocenter. We'll also generate our own synthetic DICOM images with known ground truths, allowing us to verify that the reconstruction algorithm is working exactly as expected. Why multiple gantry angles? A single EPID image only provides a two-dimensional projection. Although we can measure the horizontal and vertical displacement on that image, we cannot directly determine the full three-dimensional position of the ball bearing relative to the radiation isocenter. To recover the missing information, we acquire images at multiple gantry angles. Each projection provides a different view of the same three-dimensional offset. By combining all of these projections together, we can solve the actual three-dimensional coordinates. Coordinate convention. Before writing any code, we first define our coordinate system. Throughout this project, we'll use a consistent convention. The horizontal image offset is called du, and the vertical image offset is called dv. Using a consistent coordinate convention is extremely important because the geometry equations depend entirely on these definitions. Now let's look at the geometry. As the gantry rotates around the patient, the three-dimensional offset projects differently onto the EPID detector. The relationship is du equals to x times cosine the gantry angle minus z times the sine of gantry angle. And xyz is defined in this coordinate system as shown in this image. Every image provides another measurement of the same y-coordinate as the gantry rotates around the y-axis. At several important gantry angles, this becomes especially intuitive. At gantry 0 degrees, the horizontal offset equals to the x-coordinate. At 90 degrees, the horizontal offset equals to negative z. At gantry 180 degrees, it equals negative x. At gantry 270 degrees, the horizontal offset du equals to z. Those four cardinal gantry angles provide a very useful sanity check for the reconstruction. Least square solution. We can acquire images at any gantry angles. Each image contributes one equation. The unknowns are simply x and z because the y, we can reconstruct y simply from the average of all the vertical offset dv. For x and z, the two unknowns, once we collect enough equations, we solve the system using a least square approach. So now let's go to the code. We will use 4 synthetic Winston-Lutz images as I generated here. with ground truth. So let's walk over some key functions. One of the key functions is analyze each EPID image exactly as we developed in the previous video. We will find the field center. We will find the BB center. And we will get the offset. And then combining with the gantry angle information, we'll be able to compute the 3D offset. And here is the exact equation we will be using. And here is to use the least square function from the NumPy to solve the x and z. And for the y, it's simply the average of the dv offset. So now let's run it. It will read the 4 Winston-Lutz images. And for the first image, it will show the overlay as we shown in the previous video. The red circle indicates the field center of the center of the field, and the green circle indicates the center of the BB. And it will report the offset in du dv from each Winston-Lutz image, and then use the equation we developed earlier to calculate the 3D offset in x, y, and z, and the total 3D offset, which is the square root of the 3 dimensions. So this implementation considers gantry rotation only. In future videos, we'll extend the mathematics to include collimator rotation and couch rotation, allowing us to reconstruct the complete 3-dimensional mechanical behavior of the treatment machine. We'll also discuss how these measurements can be used to characterize radiation isocenter size, mechanical workout, and machine performance for comprehensive Winston-Lutz quality assurance. I hope this demonstration helps explain not only how Winston-Lutz analysis works, but also the underlying geometry that makes 3-dimensional reconstruction possible. If you found this video helpful, please consider liking the video and subscribing to the channel. Thanks for watching, and I will see you in the next video. Bye!